All right, Algebra 1B students, welcome to part 1 of lesson 7.7. Today we're going to talk about exponential growth, and you can join me please on page 460 in your textbooks. To begin, let's remember that an exponential equation is one that is in this form: y equals a times b to the x power. All right, and now we're going to add some formal names for our a and our b numbers, which we know can be any number that we want. The number a is called the initial amount, right? And the number b is called the base. So b for base, a for amount. A is the initial amount. B is called the base. All right, please add both of those things to your notes. That's one of the things I will be looking for when we get to class tomorrow. All right. The reason that is important is because we're going to look at certain situations where our base number, our B number, is bigger than 1. Okay, bigger than 1. And our A number, or our initial amount, is greater than 0. Right? And this is called exponential growth, because our numbers, or our y values, are growing bigger and bigger and bigger and bigger as we grow our x values as well. So this is called exponential growth. The base, the b number, is also called the growth factor. So please add that to your notes, saying the growth factor is the base number of an exponential growth equation. All right? So what are we going to do with them? Well, we're going to look at exponential equations and use them to model exponential growth in real world situations. Okay? Now, here's an economics problem, and we're going to go through this problem step by step, and then I'll have one for you to do as well. Now, the problem says, since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. Now, this part is going to probably be the most difficult part of this problem. So please keep that in mind when we talk about our growth factor number. It gives us that in 2005, about $360 billion was spent at restaurants. Okay? They want to know, right here, if this trend continues, how much will be spent in 2015? Well, that's right now. So our first job is to write an exponential function for this situation. Okay. Now we start with our general equation: y equals a times b to the x power. And now we need to figure out, what does each one of these pieces really mean? Okay. Now they help us out with this first one. But you need to be able to do this on your own as well. They tell us to let x be the number of years that have gone by. Okay, because we keep adding more and more every year, so year after year after year. That's our x number, the number of years since 2005. They say to let y, which is going to be our answer number, what we get out of this equation, let that be the annual amount spent at restaurants. So that's how much money we're spending at restaurants. Okay? What we know is our starting amount in 2005, our starting amount, or our initial amount, remember that that's letter A, is $360 billion, which we can see right over here. That's our A number. Let A be the initial amount spent, $360 billion. And then let B equal the growth factor. Now, this is where things get a little bit tricky, okay? The growth factor is not 7, like we might think, because it's 7%. we need 7% more than we had the last year. Okay, so imagine it's like this. We take 100% of last year's, and we add on 7 more percent. Okay, 100% plus 7 more percent for the next year. And if we write that as a decimal, which we do need to do, 100% is just 1, and 7% is 0.07. So here is our growth factor. 1 plus 0.07, which equals 1.07. Okay, that's our B number, or our growth factor. How much are we growing by every year? Okay, so now that we know all of our pieces, 2 of them have numbers, and then we have our x and our y as usual. We now can write our equation, which we do right down here. Our y number, how much we're spending, equals 360 times 1.07 to the x power, right? Because we continually multiply by 1.07 over and over and over again every single year. Okay. Now, let's imagine that we want to go 10 years into the future, because we don't care about 2005. We actually want to predict the annual spending in 2015. So the first question for us is, how many years has it been since 2005? Well, they tell us right here that 2015 is 10 years after 2005. So we know that our x number was years after 2005. So we will substitute in 10 for the x. All right? So instead of having 360 times 1.07 to the x power, now we know it's 360 times 1.07 to the 10th power. Okay? That's what we see in our second line. And then we do this on our calculator, and they are allowing us to round to the nearest billion of dollars. Please check this on your calculator. So, all right? Check it on your calculator. 1.07 to the 10th power. Times that by 360, and hopefully you get 708 or close to it. All right? So we can say then about $708 billion will be spent in 2015 if that trend does continue. All right? Now, if you have any questions about anything I just did, please go back through it and watch, or make a note to ask me about it in class tomorrow. All right? If you feel like you are ready to try it yourself, take a look at the Got It number 1, which is down towards the bottom of page 461. This is on page 461. And I have a new situation for you where we have 285 cell phone subscribers in a small town, and that number is increasing by 75% every year after 1985. So if we are going to increase by 75%, I will help you out with this. That means we want 100% of last year's plus another 75%. So my growth factor is 175%, or 1.75. All right, please use that as your growth factor, your B value that you are raising to the x power. And I want to know how many cell phone subscribers were there in that small town in 1994. Okay, so follow our same process, write an equation, and then insert some value for x. How many years has it been since 1985? When you are finished with that, come back and we will go on to look at one other example of an exponential growth problem. So pause the video, take a look at Got It number 1 on page 461, and then come back and join me on the next slide. Okay. The other type of exponential growth formula that we're going to look at in this video is compounding interest. And this is the way that almost all banks and loans in real life work. You accrue interest, or you get interest accumulating on your loan, and it gets to be more and more and more and more and more the longer you don't pay off that interest. Okay? So we're going to use the following formula to find the balance of an account that earns compounding interest, right? And here it is. There are a lot of pieces to this formula, so just bear with me when we go through them. You should add all of these pieces to your notes, please. The first is just A. That's the balance that we want to solve for. So we're not going to need to worry about that one too much. That should usually be our answer. Okay. P, this big red P right here, stands for the principal, which they also call the initial deposit. All right. So that is our initial amount for what in the last slide would be our A value. Okay. And then they tell us that we are going to multiply that principal, or that initial amount, by 1 plus r over n, all of that to the n times t power. Right, so it's a rather complicated formula, but the r that we see right here, that little blue r, is the annual interest rate as a decimal. So for example, if our interest rate is 5%, that means 0.05. If it's 10%, that means 0.10. Okay, so we are always expressing our percents as decimals. Right? This n that we see twice in this formula, actually, down here underneath the r in the denominator of that fraction, and again up here with our t, is the number of times that the interest gets compounded every year. For example, monthly compounding interest. Monthly would mean n equals 12. We could also see quarterly, which means 4 times per year, n equals 4. We could also see annually. That would mean n just equals 1. That one should be the easiest, or least complicated, right? And then the last one, t, is the number of years, right? Time in years. So how many years has gone by since we started? There's our t right up there, okay? So you're going to see problems here that are going to give us most of these pieces, but they're going to ask us to find an amount. Okay? So here is our first example problem. Suppose that when your friend was born, your friend's parents deposited $2,000 in a bank account paying 4.5% interest, compounded quarterly. What will the account balance be after 18 years? So you should see that we've got a lot of pieces here, 4 pieces, which is good. And we're going to put all these together in our formula from up top. Okay, so I know that my account balance is equal to my principal amount, which hopefully you can see is right here. Principal, $2,000. 2,000 times, in parentheses, 1 plus my rate, which is my interest rate expressed as a decimal. So 4.5 should be 0.045. Please remember, when your interest rate is a single-digit number, meaning less than 10, you should have this 0 right here. Okay, always have that 0 if your interest rate is less than 10%. Right? 0.045. I'm going to divide that by the number of times every year that my interest gets compounded. Well, we know quarterly, and quarterly back up there means n equals 4 times per year. So I'm going to put that on the denominator of that fraction. And I'm going to raise this up to the n times t power. And remember, n was our 4, n was 4, and then t is the number of years, which we see right here. T is 18. All right. So if you were to put this in your calculator, you should end up with 2,000 times this whole mess here is going to become 1.01125 to the 72 power. Right? And if you put that in your calculator, taking this number to the 72 power and timesing by 2,000, you should get $4,475.53. All right. Now, I want you to do got it number 2 right there in the middle of page 462. And it's very, very similar to the problem we just did. In fact, they are only going to change one thing. Right? They're only going to change one piece of your formula, and that is the compounding. They're going to make it compound monthly now instead of quarterly. So it should look very, very similar to all of this business here, all of this business. The only thing that changes is that we're compounding compounding monthly instead of quarterly. Okay. Take a look at that problem. Use your compounding interest formula. Once you've mastered that problem, you are ready for your practice problem set. Okay. So if you have questions about this compounding interest, make a note to ask me that in class tomorrow. Otherwise, that is all I have for you. I will see you tomorrow. Have a great night.